Hi class, Mr. Soule here, and I wanted to give you an opportunity to see the notes that we took Thursday in class on these diagrams that are called free body diagrams, or FBD. FBD, you'll be hearing that term a lot. That stands for free body diagrams. So let's imagine a situation here that we have a rock wall, something like this, and then we have a rock climber that's climbing up the wall, and they've got 1 foot extended, and that's up against the wall. They've got another leg that's not touching the wall. They've got a hand that's bracing against the wall. Okay. And then for safety's sake, they've got a red rope that's coming over the top and hooked on as a safety harness for them. Okay, so pretty dynamic situation, and there's lots of things going on here. When we're doing a free body diagram, what we want to do is we want to make them clean and simple, and so we are going to practice separating the diagram from the picture that the diagram came from. So separate from the sketch of the situation. And you can just use a dot as the object, or you can use a box if it's something that looks like that it's got some girth to it, like a refrigerator or a washing machine or something. But for this case, what we'll do is I'm just going to use a dot. So the climber is represented by a dot here. And then each of the forces that's acting upon that, then we're going to have to show that, and I'll put them in a different color. So I'll use red to be the different forces that are here. And each of those forces, we're going to have, sorry about this one here, but they're going to be pointing away from this particle or this dot. So when they say particle, that just means, like in the motion diagrams, we put dots down for the locations of things, and then we're going to make these vectors that show the action of a pull or a push going away from that. We're always going to use force vector arrows. So force vector arrows are going to represent that. And the magnitude of those forces is going to be shown here. And that gets tricky, but there's a workaround for that. So if we wanted to show the force of gravity acting on this climber, then we could put an arrow down because gravity is trying to pull the climber down. And then we'd put an arrow in the direction of gravity. And then we could put a number for the amount of force that's being acted there, but we'll just leave that part out right now. And the length of that arrow is going to be proportional to the size of the force. So a bigger arrow, that means there's more force. So in this case, I'm going to put a capital F, and then I'm going to put a little g to represent gravity. So every time that you put in a force, then you have to identify what that force is. And we're always going to be using the letter F, but there's going to be some subscripts. So you can have an Fg, which is the force of gravity. And then there's a force that's working opposite to that, and that's the rope that's pulling her up. So now I've got an arrow going in the upward direction. So we're going to put force, and when the rope is taut, it has tension. So I'm going to use a T there. So there's another example. Ft represents tension. And that just means that there's something that's preventing gravity from pulling her down. And then there's some more things that are going on here. Her hands and her legs are gripped into the rock. So the rock is pushing against her also. So instead of putting an arrow in this direction, because we always want to have our arrows going away from the center of that object, then I'm going to put an arrow in this direction, and I'm going to put a capital F for a force, and then I'm going to put a little f for friction. So the friction with her hands and her feet are going to be up against that rock. So this is going to be from friction. All right, so that's basically how we're going to set up these diagrams, except we're going to be doing a little bit more, and we're going to be adding numbers in, and then we're going to try to figure out the overall net force and all that. So you can add these together, okay? So you want to choose a direction to be positive or negative. And I think probably just to stay consistent with what we've been doing here is we'd put positive in this direction and negative in that direction. And so now you've got positive and negative orientations for that thing. If you had something like a skateboard, so let me draw in a realistic view, sort of. Here's the rollers on a skateboard. Here's the board part. Okay, so that would be the picture of the skateboard. And let's just say the skateboard's on one of our tables at school. So here's the table. So we just defined what the system is skateboard and table. So what I could do is I could just represent that as a block. It's easier to draw than a skateboard, even though skateboards don't look like blocks. So there's the table. And then if I want to use a different color here, not to get it goofed up, then in the center of that block, I could put an arrow down. Whoopsie, it moved over when I made a straight line out of it. There's our straight line down. And then I'm going to put an arrow down like this, and that would be the force of gravity. And then there's an invisible force that's acting on this, and it's in the opposite direction of the gravity force, and the table is actually pushing up against the block, just like the ground is pushing up against the wheels of this, except once again, we don't want to have arrows going into the object. We want to have arrows going always out of the object, the force vectors. So I'm going to put an arrow that goes in the opposite direction, all right? And then this one is the force, and this is called the normal. So anytime an object is sitting on a flat surface, or even if it's not on a flat surface, if it's sitting on a surface, comes into contact with it, then you're going to have the pushing up of that tabletop against the skateboard or against whatever's up against it, and that's the normal force. So there's another one that we would have over here, and this is the normal force. And that's kind of a new concept, and we'll be coming around to look at that more and more in the next couple days, okay? Now, so that's the basic of how we make these diagrams. How we use these diagrams and how we add the vectors in there gets a little bit complicated, and I want to make sure that you're on board with all the different steps that are involved in that, okay? So we're going to move down. It says in each case, there's a rock here, and the rock has some different forces that are acting upon it. In the first example that's shown, let me make this a little bit lighter here. We have a rock that's shown. Now this is in the example that's on the far left, and this one's already all labeled in. So the rock, and it has its center of gravity. The center of gravity is the middle of that object with a blue dot there. Okay, so then there's a rope that's attached from some ceiling somewhere, and that rope has tension on it. There's also another rope that's attached over here, and that rope has another tension on it. So that would be another tension force. And then down below, there's the force of gravity acting on it, and they use a W here. So in our notation, we would label this FT1. This one over here would be FT2, and then this would be the force of gravity, and the force of gravity, it can be called weight, and there's some of the worksheets that I got from another textbook, and they'll use W to represent that force of gravity. Okay, we'll get into how you calculate the weight of the object. All right, simple, but we'll do that in a little bit. Okay, now in the diagram here, they show that step 1, you have the weight part shown, and that's the arrow that goes straight down. Step 2, it shows that there's a length of rope. Now the rope is longer than your tension vector, and that vector is supposed to be showing the magnitude. Okay. And then what they do with this other vector that's pulling it over to the side is they add these together. Now, if you remember how to add vectors, we added them tail to tip. So they took the tail of this one and they put it up on the tip of that one. Okay? I'll show you the way to do this in Notability that's kind of cool and how it makes it easier to draw this all in. Okay, so if we move to this one here, in this example it says it's in equilibrium. So let's define what that means. Is equilibrium indicates that there's a balance of forces all together. In other words, if I add up all these forces, the force net, which is the sum of all those forces, equals 0. Okay, force net equals the sum of all forces. And there's a new symbol for that. Sum of has this Greek letter, this, and that is a abbreviation that you will see in your advanced mathematics classes once you get to doing sums of functions. Okay, so back up to our rock on the spring. Obviously, we've got some tension that's holding the rock up. So I'm going to put the tension vector here, and it's pulling the rock up in this direction. So I've got a force of tension that's shown here, and then I'm going to change color, and I'm going to put the force of gravity down here. Okay, and here's the force of gravity. And I don't know if I can draw these lines exactly perfect. In other words, the force and tension and the force and gravity would have to be equal and opposite. So what you'll see them do sometimes is they will put like 2 little hash marks here and 2 little hash marks there, and that's supposed to represent how big that vector arrow is. Now, if you put numbers in and you put 10 newtons here and you put 10 newtons there, then those would give you a number value to compare. But since we're not really using number values yet, we'll just use these little hash marks, these little tick marks on the arrows, and that shows that if there's 2 hash marks there, they're the same amount of force, even though they're going in opposite directions. So if I picked up, now let's see if I can do this. Not very good at this, but if I go and I highlight this part of it, and I copy that, and I bring the tail of this one up to the tip of this one. So I'm going to move this down, and I add them side by side. I notice when they overlap each other, they cancel each other out, so that the force net is equal to 0. And that would indicate that there's no motion, or that the motion isn't changing, and that's a sign that you're in equilibrium. Okay? Now, in this one, there's a lot more that's going on. Okay? So let's start off with the gravity. We know that gravity is going to act on the center of mass, and gravity acts straight down towards the center of the Earth. So there's my gravity force vector, and I can label that Fg. Okay? Well, then there's the normal force, and this is interesting because the normal force always works perpendicular. The normal force is perpendicular, good word, to the to the surface. There we go. That it's resting on. So the normal force here is not going to be going straight up. I'll change this to black. The normal force here is going to be at this angle because that's perpendicular, which means at a 90-degree angle to what's coming off this surface here. So then there's my force that's a normal force, okay? And then if I want to add these two things together, then what I could do is to select my scissor tool here, make this a little bit bigger. I'm going to circle this, and you have to be careful when you circle it, you get the whole thing, or it makes it a little wonky. And then I'm going to copy it, and then I'm going to go up here, and I don't have to paste it exactly in position. Oh, it hung on to part of it. Okay, so then I move it down like this. And unfortunately, it kept that line. Let me start over with that. Okay, we'll try that again. Like I said, takes a little bit of skill here. I'll start over there because it's easier to see where I started. There we go. So I'm going to go and copy this. I'm going to come up and paste it. And then I'm going to move it down. And I'm going to put it right in that position there. It looks pretty good. And then the resultant is going to be, and I'll make my resultant in green. Okay, so then in this direction here, from the tail of the first one to this tip of the second one, that would be the direction of the net force. Okay, not the neutral force, normal force, excuse me, but the net force. And this says that friction is preventing it from sliding. If there was no friction, then the rock would be moving in that green arrow direction. Okay, so there must be a friction force, and I'm going to make the friction in red. There must be a friction force in between the rock and the surface there. And so it's preventing the sliding. So it must be equal and opposite to that green arrow. So I'm going to draw an arrow equal and opposite as well as I can. And this arrow here is the force of friction. Okay? Now this one is, I got to be careful here, is the normal force. So my F net is equal to 0 because there's no motion that's going on, okay? But it would be the sum of the normal force plus the force of gravity plus the force of friction. All those things together would be added up together, and that's what's shown in the blue arrow pointing down towards the center of the earth, the black arrow pointing perpendicular to the surface of the that it's sitting on, and then the red arrow resisting the motion of that would have if it was a frictionless surface. Okay, so those are the three forces that were in play here. Okay, so as we move down to the next one, I know I wanted you to do this prior to 128. So in this case here, there's no friction in the first one. Let's make this a little bit bigger. But we do have two tensions that are at work here. So in each of the cases here, you've got a rope that's tied on. There's going to be a tension force in that direction. There's going to be a tension force in that direction. So I'm going to have two different tension forces. And then you're going to have a weight or the force of gravity in that direction. So let's put gravity in. I'll make gravity blue. I'm going to put this down in this direction. And here's my force of gravity. Okay? And then I'm going to change this to red for the tension forces. And I'm going to start here, and I'm going to come up here with one force of tension. And we'll call that FT1. And then I've got to make another force of tension because of this other rope that's there. and I will call this one FT2, and you could put a number 2 or 2 little tick marks and all that stuff. Okay. So, in other words, to make this realistic, in other words, to see if all the forces add up to 0, because once again, when it's in equilibrium, the force net, the sum of all the forces, is 0. So if I add all these up together, let me show you how we make that parallelogram. I would go and take one of the forces of tension. Let's take this one. And I'm going to copy that one. And I'm going to move it up and I'm going to paste it in position. Oh, it took too much of it. Darn it. I have to get rid of all that. Oh, I guess I didn't have to get rid of all that. Let's try this circling again. If you don't circle the whole thing, it just keeps going and grabs everything that you've drawn on there. So we go and we copy, and then we paste, and I got the whole thing again. So I'm going to get rid of the blue part and that red part. Okay, well, that works. Except now, oh my goodness, how do you do that? Well, oh boy. Let's paste another one in there. Let's move this down here. Here's the workaround. Okay, so I don't like how that looks either. I'm sorry. It doesn't seem to want to just grab part of this. One more time, Sule. See if we can get that. No, it doesn't want to do that. All right, so I'm just going to move this down and put the tail to the tip, and then I'll see if I can't erase these other 2 lines. There we go. So this is the beginning of my parallelogram. So the parallelogram then would be if I add this one on here, here we go. There's a parallelogram. And so the total tension from these 2 ropes is going to be the sum of those vectors that goes from, and I'll do that in black, it's going to go from the tail of the first one to the tip of the second one. So if I go up and I go straight up like that, then here is the sum of the tension vectors, and it should be equal and opposite to the force of gravity. So if I put 2 little tick marks here and 2 little tick marks there, it means that the tension on the combination of those 2 ropes is exactly opposite to the tension on the, not the tension, but the force of gravity on the rock. Okay, and that means that that rock is not going to be moving, or that there's a balance of forces. Okay, balance of total forces. All right, so for linear motion number 5, equilibrium, I'm going to just set some of the things in here. There's going to be tension here, there's going to be tension there, and then there would be the force of gravity here. See if you can't fill in the parallelogram to make that complete. And then in the last one, you're going to have a gravity force here, and then you're going to have a normal force there. And those should be equal and opposite if it's going to not be sliding, falling, or raising. Okay? Hopefully that gives you some overview of all that, and that you see that there's going to be a net force that's acting on those. Okay. If we go down to the bottom, now you can do those other 2. We did those in class. That'll be kind of an exercise for you. Now, these are a little bit different because we've got some combination of forces that are working here. If I'm just going to highlight these forces, I've got the force of gravity going straight down. I've got a tension force that's working in this direction, and then I've got a normal force that's working in that direction. So let's label all those. So here's the force normal. Here's Fg from gravity, or we can call that W. And then here's the force from tension. Okay. And if I put some of these values in, and I say the normal force that's pushing up on the rock here, let's say that it's that much, okay? And then if I take, let me change the color of this to purple, the tension force, and if I put the tension force in this direction, there's the force of tension. And if I circle my tension force, copy that, paste it up here. Once again, it's not cooperating. And I add it tail to tip. Let's get rid of that extra red line. Okay, so then I built a parallelogram, and the net result of the tension and the normal forces then, I'll make it green, is going to be this, and it'd be going in that direction. And if you use your wild imagination, you'd say, oh, well, that would have to be equal and opposite to the length of the gravity vector. Now, the way I have this drawn, it doesn't show that it's exactly in the same angle. That's okay. That's going to come with practice. Or if I gave you some numbers, then it'd be a little bit easier. But if we just put 2 tick marks here and 2 tick marks there, then that's a good start for making these free body diagrams, because you've got everything labeled. You've got your force net equals 0. That means there's not going to be any motion. It's labeled that it's in equilibrium. Okay, you've got your normal, your tension, and your gravity forces labeled. And then you've shown me your parallelogram, where in actuality, if I was going to, if we wanted to make this a little bit more exacting, I'd have to rotate it up somehow. Copy, and then if I get rid of that one, oh my gosh, how do you do that? See if I can do that. Oh, got rid of all of it. Oh, wow, I'm sorry. Let's not do that. Where in actuality, it would be exactly in the opposite direction if we were drawing it a little more carefully to your force of gravity, okay? And this would have the 2 tick marks along with those, okay? All right, so my bad, I didn't draw those arrows to the right magnitude. This one shouldn't have been quite so long, but I think you see the overall idea. And labeling the forces, that's the incredibly important part. Let me get you started on the next 2 and show you where those forces are going to be. Because once again, we've got a downward force here that's going to be gravity. Now, we've got a normal force that's acting on the base of the rock and the shelf that it's sitting on. So perpendicular to that is going to be going in this direction. And then I don't have tension, but I have another normal force that's working in this direction here, but I can't put arrows into the rock, so I would put an arrow coming out of the rock in that direction. Okay, so if I start from the force of gravity, and let me make gravity blue, and I say, here's my force of gravity, Fg, then I know if this thing isn't moving, then my combination of those forces must be equal in magnitude, but in the opposite direction. So this would be the combination of the 2 other tension or normal forces that are there. So let's label those. Here's a force normal 1, and here's force normal 2. And then I'll leave it up to you to see if you can draw in arrows that when you add those two vectors together, you start here and you end up there. A little exercise for you. Okay. And then the last one, in this one, it's sliding. Well, if it's sliding, then it's not in equilibrium. And if it's not in equilibrium, that means the force net does not equal 0. So that means there's going to be a little leftover force, and that force is going to be in the direction of the motion. So the resultant is in the direction of motion. All right, and since this thing's going to be sliding down an incline, we know the resultant, and we'll make it hot pink. It's going to be moving in this direction. So there's my resultant. And that means that the combination of all the other forces then will have to add up to that pink arrow. So let's see if we can identify them. One of them is going to be gravity. There's my gravity one right there. And one of them is going to be a normal force. So there's my normal force right there. And if I go ahead and label these, and let me see if I can't rough in one of them, we'll use blue for gravity again. So I'm going to make my gravity vector here the force of gravity. And then let's see if I can't let's make this one orange. Okay, so we make this one orange like this. And there's the normal force that's acting on this. So here's the force of normal, which is pushing against the bottom of that rock by the shelf. Now, if I lasso, I don't know if I made these quite the right size, but if I lasso this one, let's copy that. And then I'm going to add the tail of that to the tip of this one. Oh, look at that. I go here. I put that one right there. Okay, good. Then my resultant, let's get rid of that. Then my resultant is going to be, let's make that hot pink again, from the beginning of the orange one to the end of the blue one. So there's my resultant. And it's in the direction of motion. Okay, now it wasn't exactly parallel to that shelf, but that's because my parallelogram wasn't exactly proportional to it. Okay? All right. The idea is that you're adding vectors, and when you add the vectors to get the resultant, and when you're doing this in 2 dimensions, you're going to be using parallelograms. I don't know if that's how you spell parallelogram, but that's a really big word. Awesome. Okay, and that's the bottom of the sheet. Hopefully that was helpful, and we'll see you in class next time. Bye, guys.